Hi everybody, I would like to present a work of this year in which we developed a reinforcement learning based controller for autonomous multi-rotor landing on moving platforms. The motivation is that multi-rotor vehicles have proven to be useful in many scenarios. However, they suffer from comparably limited range and flight time, which is for example required for missions like the observation of wildlife over a longer time span. One approach here is to enable the UAV to autonomously land on a moving carrier platform that provides equipment to replenish batteries and offload data. Classical controller design often requires accurate and complex models of the vehicle and the environment. Reinforcement learning provides an attractive alternative due to its ability to learn a suitable control policy exclusively from interaction with environment during a training procedure. But current methods that address the landing task by leveraging deep reinforcement learning techniques to control the coupled motion of the UAV require several hours to train, have limited success rates, and depend on hyperparameters that need to be tuned by trial and error. In our approach, we address all these issues. To this end, we decompose the landing procedure into a sequence of simpler but similar learning tasks. This is enabled by applying two instances of the same reinforcement learning-based controller that has been only trained on one-dimensional motion of the UAV and the platform. The first instance controls the longitudinal, the second one the lateral movement of the UAV. The vertical descent as well as maintaining a fixed yaw angle of the UAV are taken care of by PID controllers. For the training on the one-dimensional movement, we introduce a powerful state space discretization technique that is based on the notion that accurate information about the relative position and the relative velocity between the UAV and the platform is only required when landing is imminent. Our approach leverages a multi-resolution discretization technique in combination with transfer learning as part of a sequential curriculum to accelerate training. Furthermore, we leverage a kinematics model of the moving platform to also derive interpretable hyperparameters for the training procedure that ensure sufficient maneuverability of the multi-rotor vehicle. For the training of the different curriculum steps, we apply the tabular reinforcement learning method double Q learning. The further the curriculum progresses, the higher gets the achievable accuracy with which the UAV is able to center above the platform. We extensively tested the approach in simulation first for different scenarios, such as a static platform, a rectilinear periodic movement, or an H-shaped trajectory. Last but not least, we conducted experiments on real hardware. Our results show that our approach leads to a higher number of successful landings while requiring less training time compared to a baseline method that uses deep reinforcement learning.